go over this example up here. So let me get my mic connected. And I can show you how we can do this. All right. Okay, so the example that I gave you had the failure time of 20 identical component, and the idea is here we want to use this information to set up the reliability PDF probability. The probability distribution function, and then reliability, and we want to calculate the failure rates. And eventually, I ask you to set up the plots for each of these elements. So let's look at the data that we have. The easiest way in Excel to look at the histogram of data is to use the analysis tool pack that exists in Excel. If you're using Mac, you have to go to Files, Options, Add-ins, and within your inactive or in the tool add-ins that are not enabled, you have to pick Analysis Tool Pack and add it to your system. If you're using Mac, then you have to go to Tools, Add-ins, and then there are two add-ins, Analysis Tool Pack and Solver. You want to check mark Analysis Tool Pack and hit OK. If you do that, under the tab, Data tab, you have the Data Analysis Tool Pack available to you. So if I click on this, there's an option histogram here. For histogram, if you click OK, it allows you to choose the input range and bin range. So right now we have 20, you have 20 observation, and the time for testing these 20 components seems to be between 0 and 20 minutes. So the number of interval in this case is going to be 1 plus 3.3 logarithm of 20 in the base of 10, which is 5 point something, and if you get the integer part, it becomes 5. So you need 5 range. And if I consider 20 minutes for the amount, the period of testing, it means I have to divide my time interval 20 into 5 into a different interval. And the way that Excel works, you can define your upper range and put it in the system to calculate your frequencies. So the first range I ended at 4, starting from 1 to 25 divided by 5. Each of them is going to have a width of 4 minutes. Next one is going to be 8. Next one is going to be 12, 16. I can end it here because typically Excel add a category as more after the last digit that you put in. Or you can just put 20 and your more interval is not going to include anything. So what is the meaning of this? It would include anything up to 4, including 4. So let's look at the data analysis tool pack and then go over to histogram. It asks you what is the range of data. You click and select the range of data. And also it asks you for the bin range. If you have any, then in this case we do. We select it. And then if you click, make sure that you check mark chart output, otherwise it doesn't generate the chart for you. So there is a chart. Bin range is the part that I entered for 8, 12, 16, and 20. That's the upper bound of your intervals, basically. If I hit OK, then it generates the charts in addition to frequencies for me. So it says the first one, including 4, as I said, that includes, so basically the first bin is X from 0, let's say, up to 4, your time, including 4. That's the frequency related to that. The second one is going to be your time is between 4, not including 4, but including 8. Next one is from 8, not including 8, up to 12. And next one is from 12 to 16. And last one is from 16. As I said, Excel always generates another category as more. You can ignore that because right now our more category has 0 frequency. We already included everything in there. Now, what I want you to do, does it look like a histogram here? Yes or no? No, this is a bar chart. there is no gap in a histogram. So you have to double click on these bars. When you do that, there is like an option in the side that appears that allows you to right hand side to remove the gaps. So when you click on the bars in the right hand side control panel, you can bring the gap width to 0 to get a histogram. Otherwise, it doesn't look like a histogram. Now the question is, does it really look like a exponential distribution? It seems that up to fourth interval looks like follows the exponential distribution pattern, but toward the end, we also see toward the end we have a high frequency as well, which is actually true for a lot of real life experiment, because the chances of failure at the beginning and end of the system, end of the length of the system is really high. If you remember, we had a bathtub curve for the reliability, and you can see that here, because the frequency when the system, have you ever heard that the probability of failure when the airplane takes off or lands is higher at the beginning, at the end of the system operation, the odds are higher. So that you can see it here. You see the frequency at the beginning and at the end is much higher, because it takes time to system reaches to a stability condition. When the system is within the, not in the boundary condition, within the stable kind of situation or environment, the odds of failure is much lower. So now we have this frequency histogram. That's the initial point. Now how can I use these frequencies to calculate my FT? If you remember, what is the equation for our FT? What is the equation here? Number of failures in the interval divided by n, which is 20, divided by delta t. Our delta t is equal to 4, and our n is 20, and we have the number of failures each time because we have the frequencies that are given. So it's going to be frequency divided by 20 multiplied by 4. And I drag this formula along for the 5 categories of observation I have. Next time I can calculate lambdas, and I can calculate R after that. So my lambda here is going to be number of failures in the interval divided by the number of operating at the beginning of the operating unit at the beginning of the interval. So for that, I'm going to insert a column here that gives me N0, which is the number of number of operating unit at the beginning of the interval. So how many units are working at the beginning of the interval? We have that we start with 20. After the first 4 minutes, 6 of them fail. So you're going to have 20 minus 6, which is going to give you 14. Then you're going to have 14 minus the next 4 that are failing. And if you drag this formula, you can calculate the number of units that are working at the beginning of each period. Do you guys have questions? Yeah, go ahead. Okay. So then you have lambda. Lambda is by dividing the number of failures in each interval, which is given 6, for example, in this case, divided by number of operating unit at the beginning, multiplied by delta t, which is 4 in each case. So that becomes your lambda for each of these scenarios.
Wait, isn't it 6? Well, for yours is 4. For ours is 5, right?
This is for lambda, and if your frequency table is different, your interval are different, this is going to be a slightly different.
Yep.
So your RT is going to be the number of units that are working at the beginning of each interval, which we calculated here, divided by total number, which is 20, and it gives you the reliability. Now I can look at the reliability and see how it works. I can select this, and if you go under insert and add a kind of plot a line, you see that your reliability is exactly exponential. You see that? Seems like a very smooth exponential function. As as the time goes by, the odds of failure drops. So it looks like a exponential form here. You can also take a look at your lambda or failure rate. If you select this and if you go under insert and add a line chart here as well, you see that your lambda is kind of going upward. The failure rate is increasing. Now, if you put these two on top of one another, you get the bathtub curve, which is kind of shown in the f of t, which is here. So this is how you can calculate the reliability of your component. If I ask you what is the probability that the system works for 8 minutes, what is the probability that component works up to 8 minutes? 70% is going to work up to 8 minutes. Any other question for this?
Wait, how did you come up with 8 minutes?
So T from 0 to 8 is 70%. Okay. All right, so that's how you can work with the experimental data to come up with reliability answers. So if you want to define, so using these probability, you know what are the chances that your component works for a certain amount of time. Now this is a very simple example to just like give you a kind of starting point, but if you really assign to define reliability, designing the experiment for testing the component by itself, it's another task that requires design of experiment, ANOVA, and so forth. Have you heard of design of experiment? No? Okay. So if I want to test the component for its reliability, one thing that you have to make sure that you have to fix everything else besides what you're testing for. Basically, it means that if I want to see the length, how much this marker is going to work, I have to fix everything in the control environment. So there is no difference from testing one component to the next one. I'm not testing the first component in hot and humid and the second one in the cold weather. So they should be tested in a kind of consistent environment. In addition to that, you want to test the impact of different things on your component as well. For example, the angle that the person uses for this marker might make a difference in terms of the length of this, the life of this marker. So let's say if it's too high up, it might last shorter than if it's like in a vertical angle or perpendicular to the board, or the different things. So how do I know if different factors have different impacts on the length of the life of this marker so I can set my warranty policies? You see that if they say if you use this product in this condition, we don't guarantee, or is out of warranty, because at those condition, at those temperature or environment, the tests that the tests that have been implemented for defining the warranty is no longer valid, right? So can you give me an example of such component or something that you used in a way that it made it that is not eligible for warranty anymore? Phone. Okay. So what are the things that are not considered, that wasn't used to be a part of the phone warranty? For a certain time, the battery is under warranty as well. But let's say, so your phone before, let's say before iPhone was able to create some, iPhone 7, which is kind of water resistant to some extent. If there was like, if your phone fell in the water and there was like a thing that would show it would turn into pink, and therefore it wasn't no longer a test condition, right? So there are things that define in your warranty, which is based on the test condition, test environment, that kind of dictated the amount of time that you're going to set your warranty time. So you have to be mindful of those ones. Now, if you guys don't have any question, the next thing that we're going to go over, I'm going to give you a few minutes break, and after we come back, we're going to go over the next part, which talks about other mode that we can use to test our, basically define the failure mode. So far we learned FMEA, right? Failure mode and effect analysis. And we learned how we can define reliability and use experimental data to define reliability. And after that, we're going to learn other method that helps us to define root cause of some sort of incident or failure in the system. And After that, we learn the fault tree analysis. Basically, we want to define minimum cut set. In minimum cut set, the idea is to define the minimum set of components that their failure leads to immediate failure of the whole system. So what are the components, for example, in your car or in your phone that if they fail, the system is going to definitely fail? That's called a minimum cut set. So that's a very important idea that we're going to cover in the next session. If you guys don't have any question, we can go and for a break and recess in like 15 minutes.